Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of the Astronomy Department here at Foothill College in Silicon Valley, and it's my great pleasure to welcome everyone here in the Smithwick Auditorium and everyone watching us on the web to this lecture in the 19th year of the Silicon Valley Astronomy Lecture Series. This program is co-sponsored by the Foothill College Science and Math Division, by NASA's Ames Research Center, by the SETI, or Search for Extraterrestrial Intelligence Institute, and by the Astronomical Society of the Pacific, all of them organizations which are devoted to the public understanding of science. Tonight's speaker is Dr. Brian Keating of the University of California at San Diego. Dr. Keating is a cosmologist and the principal investigator of the Simons Observatory collaboration in Chile. He's the author of more than 100 scientific publications and 2 US patents. He was a postdoctoral fellow at Stanford and Caltech and received a 2007 Presidential Early Career Award for Scientists and Engineers for his role in inventing the BICEP telescope, which he'll tell you a lot more about tonight. Dr. Keating is a commercial pilot with multi-engine instrument ratings and is a trustee of the San Diego Air and Space Museum. But he's here tonight because he is the author of a popular book called Losing the Nobel Prize, and he will be signing copies of that book in room 1401 after the lecture and the questions are over. I wanted to mention that just recently, Losing the Nobel Prize was selected by Amazon as one of the top science books of 2018. So he's going to talk a lot about the pressures of the Nobel Prize and the amazing work they were doing at the South Pole. Let me now introduce to you Dr. Brian Keating.
When you think of the most important astronomical phenomenon, what comes to mind? A black hole, a wormhole, some other kind of hole? Well, let me tell you tonight, we're going to talk about what I consider to be the most important substance in the universe, and it's nothing more than what follows around most of our children, which is dust. Except I'm going to explain to you how dust played such a phenomenal role throughout cosmic history, astronomical history, including some of the biggest discoveries ever made, and some of the undoings of some of the seemingly biggest discoveries ever made, including one that I was intimately involved with, as I'll describe. And I'll explain how dust destroys things such as Nobel Prizes, but it also creates things such as planets, and even creates the hemoglobin that's flowing through your veins right now. And I'll explain the cosmic web that connects all these things together. But as Andy mentioned, I'd like to thank Andy and Foothill and the Astronomical Society of the Pacific, and the SETI Institute, NASA Ames, and my mother and father for having me. No, there's so many people I'd like to thank. It's so nice to be here back in the Bay Area. And I commend you all for braving through a cloud of dust on your way to get here. Now, when I was a kid and I used to read books by Isaac Asimov and other science authors, science fiction authors, I used to always get dismayed by the dust jacket. I used to hate dust jackets. This is what happens to dust jackets. So I get a stack of books delivered to me as a first-time author, and as soon as I get them, I open them up and the dust jackets fall off and the book comes out and they curl up, wrinkle up. And I used to think, well, this is kind of unusual. Why do we have dust jackets? And then I realized something really interesting, because you think about things like black holes and wormholes and gravitational lenses and all sorts of things when you think about astronomical objects, but there's a reason that books come with a dust jacket and not a wormhole jacket, okay? Because dust is much more ubiquitous. It's much more commonplace. And it actually plays a vitally important role in our lives. So although I don't really like dust jackets very much, they did a nice job on the dust jacket that we'll be presenting after the talk tonight. So I'm going to talk a lot about the Nobel Prize. Before I get to the Nobel Prize, I want to just explain the scientific project that I was involved with at the bottom of the world in Antarctica. And this project set its sights on the very cosmic prologue itself, namely the conditions under which the universe's Big Bang unfolded, which remains shrouded in mystery until this very day. I want to explain why that's so important And I want to motivate the searches that we undertook, in part motivated, at least speaking for myself only, motivated by an award created about 125 years ago by none other than Alfred Nobel. And Alfred Nobel did something amazing. With his will, he revitalized the Nobel name, which for generations had been associated with basically arms dealerships, that they were the foremost creators of military explosives, which they sold around the world to the highest bidder. In fact, when Alfred Nobel's older brother Ludwig died in 1888, there was a newspaper article headline in the Parisian newspaper where Alfred Nobel was living, and it said, "The merchant of death, Alfred Nobel, is dead. The man who single-handedly caused the deaths of more people than any other man in human history has met his just reward," or something like that. Now, obviously, he's reading that, so it can't be him, right? So it's like Mark Twain, the reports of his demise were slightly exaggerated. In this case, though, it did something for Alfred Nobel that was essentially the same phenomenon that happened to Ebenezer Scrooge, which is that he got a taste of what the world really thought about him and what they would say about him after he died while he was still alive. And he set out in 1888, he wrote down his will a few years later, and he decided to take essentially all of his war profits, the profits that he and his family had accrued from making things, the most profitable of which was dynamite, using that vast fortune to make the world better through a series of prizes that he endowed that bear his name. And I'll talk a lot about that and how that sort of was very fortuitously timed. And actually, his will was written in November of 1895, and he died a year later. And there's a saying that you should always do penitence the day before you die, right? Of course, you don't know when you're going to die, but he got pretty close. He got within a year of his death, and he actually endowed this will that launched this vast public relations coup, in a sense, that I claim is really the most famous will ever written. And what impelled me on the quest that I'm going to describe tonight is in part the desire to win this 24-karat gold medallion, cash value $24,000. And as I was a young cosmologist, when I came up with an idea that I was assured by many people, if it were successful, would result in my having one of these to hang around my neck. I'm going to describe that quest and the project that I hope would bring me to Stockholm to win this award, and how it was essentially lost. Hence, one of the meanings of the book's title, Losing the Nobel Prize. It's not a how-to guide, okay? I don't want anyone out here who's about to win the Nobel Prize, to use it as a how-to guide to lose. But I like to say that, most people don't get to the promised land, whatever that may be for yourself, right? You don't get to be president or governor or whatever. You don't even get to be, a high school class president for some of the young people. So how do you deal with setbacks, with adversity? And how do you resolve to make improvements, both for the benefit of yourself and your own career and the people around you, but maybe for the world as well? And that really is the catechism of the Nobel Prize, for the betterment of mankind. But I want to start with the first astronomical telescope, wielded by Galileo Galilei himself. This was a lever that really was a short lever in a sense, Archimedean sense, but as the saying goes, given a long enough lever, you can move the world. Well, this tiny telescope, barely longer than an arm stretched at arm's length, was enough to displace the world, the entire planet, from the centrality that it had enjoyed for millennia before Galileo's observations in 1609 and 1610. This is what he saw, and he sketched it so beautifully in Sidereus Nuncius, the Starry Messenger. And I actually got my hands on a copy of this not too long ago, courtesy of my friend Jay Pasikoff, who is, I'm sure, familiar to many of you. He wrote the book, The Field Guide to the Stars and Planets, which was the very first astronomical text or field guide that I ever read as a 13-year-old. And so it shows in that book, in that masterful book, Galileo's talent at data science, the science that many of you in this valley made of silicon practice, which is to express findings that are quantitative in sometimes a qualitative form. And in doing so, make an argument, in Galileo's case, a scientific argument, through pictures and through simple words, descriptions, and mathematics. That was enough, as I say, to displace an entire planet from being the center of the universe. But Galileo, like Einstein, was also not, he was mortal. He was not free from making errors. And one of his errors, which I consider to be his biggest blunder, I'm alone in this assumption, by the way. Many other people claim that his biggest blunder was actually his theory of the tides, which I discuss in my book, but I won't get into that now. But many of you may recognize this tiny asterism. You can see it tonight through the haze, through the smoke, through the dust. And it's the Pleiades, or the Seven Sisters. And you may, if you speak Japanese, refer to it as Subaru, which essentially means the same thing. And you know that it's called the Seven Sisters, but you don't have to be very good at math to count up 6 stars there. So no, the guys at Subaru and gals did not make a mistake. There are actually only 6 stars that you can see with the naked eye. But with a telescope, even a tiny one, even a 2-inch diameter refracting telescope that Galileo used, did not invent, but used, improved, and made great advances with, Galileo was able to reveal the Pleiades in a way that had never been seen before. He saw countless stars, not just the 7 stars that you could potentially see on a good night with perfect vision and no alcohol in your system, or the 6 stars that most of us can see if we're fortunate to have relatively good vision. But he saw basically an uncountable retinue of stars. And he sketched it here in what Edward Tufte has called the first and best example of data science in human history, which was to make an argument, a scientific argument, by way of a depiction, a graphic. So Galileo was an artist, and the Pleiades, like all artists have their muses, Galileo's muses were the Pleiades, the nurse nymphs of Dionysus, the god of the grape. And when he sketched it, he sketched these filled-in stars here and these open stars. And the difference was the filled-in stars were stars that he could only see with the aid of the telescope, or as he calls it, a spyglass. And he says down here, what was observed is the nature of the matter of the Milky Way itself, the galaxy itself, which the spyglass reveals so well that the disputes that for so many generations have vexed philosophers are destroyed by visible certainty. And we are liberated from the philosopher's wordy arguments. So I love this because it shows a physicist making fun of a philosopher. Okay, we all do that. We all physicists like to make fun of philosophers. But he's also making an argument that by visualizing something, you could prove a scientific conjecture, which was that the glowing, mysterious glow that surrounds the Pleiades was actually comprised of stars that his telescope could not resolve, but it could if he had access to a bigger telescope, which he never actually made. And so he never actually verified that his conjecture was false, and therefore it was a blunder. Because if you have access to the Lick Observatory, if you happen to have one of those nearby, you can go out and you can take an image, a long exposure, with a much bigger optic, and you can never resolve the glow that's here into individual stars. So, blunder. But in the same sense, he was making the argument that this glowing nebulosity was representative in just the same way that the Earth was a mere planet, that the stars in the night sky and the sun itself was just a mere minuscule element to the vast cosmos at large. He was making a scientific argument, and he said by visible certainty, essentially proof by visualization. And we have another name for that now. If you zoom in on the nebula here, you can never resolve it into individual stars. In fact, what it resolves into is what's called a reflection nebula. This M45, for all my astronomer friends out in the audience. M45 has this beautiful glow that suffuses it, that under any amount of magnification remains this diffuse glow. In fact, if you have a Hubble telescope at your disposal, you'll see these knots here. And these knots, the nebula, is actually tiny mirrors that reflect the light from the star. This is Merope. And reflected light has the exact same spectral chemical fingerprint as the star itself. Therefore, these elements are reflecting the light. They're not individual stars. It's dust. And that's what the nebula is primarily comprised of. And some of these knots of dust are not so different from what our primordial solar system must have looked like from afar, in that it was comprised of gas and dust. And there were stars that were illuminating it not too far away, and perhaps the sun had a companion, perhaps it didn't. But that starlight reflecting off of the nebular dust is what confused Galileo into making, Brian Keating's opinion, his biggest blunder. Now, he still was renowned for making some not insignificant discoveries in his career, despite that vast blunder. I'd be happy if I made a blunder like that, by the way. With the telescope, he displaced the Earth from being here to being here. A movement of 93 million miles, right? But at the same time, a complete revolutionary idea for humankind, that we weren't the center of the solar system. And the solar system and the stars are basically in the entire universe. They didn't know yet about stars in other galaxies, as that would come about 100 years later after Galileo's time. Nevertheless, he enjoyed some success. So the first bit of success he had made him very enviable among professors such as myself. He took his telescope to his funding agency, this is the Venetian Senate, and they said, that's a great piece of technology. We can use it to spy ships entering the Venetian lagoon and thus destroy the stealth advantage that they would otherwise have. This was of great value to them. They said, let us do the following in exchange for you giving us copies of your telescope. Let us give you full professorship, tenure, and we will double your startup request. So that's pretty good. Where's Jeff over here, the astronomy faculty here? So anybody would trade that gladly for a couple copies of a telescope that nowadays you can buy online for under $50. So he had a great need for cash because he had many illegitimate daughters. A famous book by David Sobel called Galileo's Daughter tells these stories of how Galileo really needed to keep up this monopoly that he had on making these powerful astronomical and military telescopes. So he enjoyed the fame that the Sidereus Nuncius brought him, and for a while it was all good because he was basically doing what I'll be doing later on tonight. So he was doing book signings. That's always fun to do for any first-time author. But later, the position that he had been offered on the tenure track was in Padua, which was within the realm of influence of the Vatican. And the Vatican wanted him to disavow the teaching of Copernican theory even after the publication of Sidereus Nuncius. But Galileo, he had a little too much cosmic hubris. And what he did is he refuted that decision made by the Pope, Pope Urban. And he said instead, no, I'm going to keep writing about this. And finally, he wrote a book called The Dialogue, or Dialogo, in which he contrasts and compares the models of Ptolemy and Aristotle with the model that he and Copernicus had promulgated. So he put the arguments of he himself and Copernicus in the words of a single character named Salvati, which means the brilliant one, I'm told. And the arguments of the Pope and Aristotle he put into a character whose name is Simplicio, like the simpleton. Not a good idea, okay, out there. So this resulted, eventually, he was brought in front of the Holy Office. Again, a euphemism. In the same way, as I always say, the IRS is a euphemism for money donation service, okay? This is not, they had no interest in kind of seeing what the telescope could provide if they put their eyepiece at it. So with Galileo's telescope, he went out to here, hundreds of light years from Earth. And then beyond that, the next set of astronomers, such as William Herschel, turned even vaster telescopes to the galaxy at large, and again made a similar proposition to what the pre-Copernicans had made. Namely, they said, we may not be the center on Earth of the solar system, but the solar system is the center of the galaxy, or pretty close to it. So here's a representation of Herschel's image of the Milky Way, and he put the Earth at the center, or close to the center, of the solar system near the center. Now, the reason that he did this is also related to the properties of cosmic dust. And I want to explain how that comes about. So the very same substance that befuddled one of Galileo's and caused his biggest blunder, in my less than humble opinion, leads to a couple of factors that conspire to cause astronomers to make blunders and errors to this very day, okay? And so spoiler alert, dust is going to keep coming back in this talk. I'm not going to talk about wormholes or multiverses. I could, but I'm not going to. I'm going to talk about dust, which you may think is really boring. I hope to convince you it's really interesting. Okay, so I'm a dust expert. So I spend my days researching dust. Now, if you look through a mirror, a window that's dusty, you will see a same amount of light diminished. And that will cause you to impute a distance to the object, the same exact object, the same luminosity, same intrinsic brightness. You'll attribute and ascribe a greater distance to it. So dust diminishes the intensity of light. It causes you to overestimate how far away the objects are. That's one error that contributed to why Herschel made the picture that I described, where the Earth and the solar system is near the center of the galaxy. The other thing that dust does is redden the light, make the light red. How many of you saw the beautiful sunset tonight on your way down here? I saw it earlier today. It's just phenomenal. It looked like this. This is taken from San Diego. So this image here shows the sun near the horizon. This image here shows the sun at zenith. Now, does the sun change in the 6 hours between noon and sunset? Of course not. What changes is how much dust is in the atmosphere it goes through. And even the sunset tonight during these terrible fires in the season in California, even the sunset tonight is even redder than this image shows of the sun over the ocean, say. And that's because there's much more smog and smoke in the atmosphere And the more atmosphere you look through along the tangent plane towards the sun's set, the more dust you're looking for, the more reddening and dust diminishing that it gets accomplished. And dust also does something else. It makes the light polarized. It tends to orient the light, at least in our galaxy, in a very unique orientation. I'll describe that. So what caused Herschel's illusion was that he didn't realize we're actually out in the outskirts of the galaxy, about 2/3 of the way out in our galaxy. And just like you feel when you're inside of a cloud on an airplane, it kind of looks like the cloud is centered on you. So as you heard, I'm a commercially rated pilot. I don't fly people commercially, but in case you're wondering, it's just for fun. But when you are looking out the cockpit of an airplane, or even in the passenger seat of an airplane, and you're inside of a cloud, it seems like the cloud is centered on you. Even though the cloud may have a very strange shape and not be centered on you, you may be somewhere over there. The same phenomenon happened in our galaxy, and still does. And it caused Herschel to feel like all the light was diminishing in every direction he looked, and it looked like it was centered on him. Therefore, we must be at the center of the galaxy. So that was wrong. We're actually, as I say, about 2/3 of the way out. Here's the galactic image that we know about today. They're objects like globular clusters, which Shapley and Curtis used to actually find the actual center of the Milky Way being towards the constellation, in the direction of the constellation Sagittarius. And we're somewhere out here, about 2/3 of the way out on the Milky Way's radius. So quite far off from the center. Again, dust creating a mirage, tricking astronomers into the illusion that they're somehow central and important in the organization of the cosmos. Let's fast forward 400 years, because we only have an hour tonight. And the discovery of the cosmic microwave background, made in central New Jersey, one of the best discoveries, the best things to ever come out of New Jersey. I can say that because I'm a New Yorker. I like to tease you guys. And this discovery was really found serendipitously, which I claim is the purest form of scientific discovery. When you find something that you're looking for, there sometimes is a bias called confirmation bias. Just like Galileo wanted to buttress the Copernican theory, so too do astronomers or scientists of any stripe who want to prove a theory fall into the trap of confirmation bias, namely discarding evidence that disagrees with you and accepting evidence that agrees with you, even if it's not justifiable given the evidence that you have. It's a very pernicious phenomenon, and it affects cosmologists as well as any other scientist. In this case, they discovered it accidentally. They were trying to communicate with the first telecommunications satellite, found an irreducible set of amount of noise that they could not get rid of no matter which direction they looked in, no matter what season they looked in, no matter what time of day, even if they looked at New York. Even once they cleaned out a family of pigeons that had deposited a white dielectric material inside of the antenna, they still could not get rid of it. And the only decision that could be made after consultation with their neighbors and competitors at Princeton was that this glow must be the afterglow of the Big Bang. The leftover heat after the formation of the elements in the first tens of minutes after the origin of the universe. And so I like to say that these elements, they're forged in a time period less than it takes to watch the sitcom The Big Bang Theory. All the elements that make up the elements that form stars, namely hydrogen, helium, a little bit of lithium, etc., the lightest elements, all of that would ever form in cosmic inventory was formed in this tiny period of time, less than a sitcom in length. Just phenomenal to think about. Now, fast forward another 50 years or so, and my friends at NASA and my friends at the European Space Agency have made exquisite maps of the entire microwave background, amplified the contrast in those images so that you don't just see a uniform 3 Kelvin glow, instead you see tiny fluctuations. The fluctuations are only about 100 parts per million. To give you an idea of how minuscule those fluctuations in the amount of heat energy we receive from cosmic distances, if you look at a bowling ball has fluctuations that are 10 times, so 1,000 parts or a part per 1,000. So they're bigger fluctuations in the surface of a bowling ball, especially my bowling ball has a lot of dents in it. But a bowling ball, which you think of as smooth, has fluctuations that are much, much rougher in a sense than the microwave background. That's how exquisitely polished the uniform universe is. So how did we get to be here? This is the Hubble Ultra Deep Field. How did all these structures get to be here? Some of these things are billions of times more dense. So the fluctuations are not parts per million, they're billions of times bigger. So you're talking enhancement factors due to gravitational collapse of factors of trillions upon trillions. So how do these tiny seeds, these fluctuations in this pattern depicted on this beach ball here, how do they grow into the clusters of galaxies that Hubble would see after, say, a few 100 million to a billion years in cosmic history. They grow under gravitational collapse. But how did they get there in the first place? The best candidate for a theory that describes how seeds could be planted in the universe at a time when it was just after its origin, that could then plausibly grow under gravitational collapse to form these gravitationally bound structures called galaxies and clusters, is called inflation. I want to talk about inflation and make an analogy that will be a lot more familiar, perhaps, to some of us in the audience. And that is, we're trying to see the universe as it is about 500,000 years after, or using the picture of the universe that we, my colleagues and I, take of the universe as it was 500,000 years after the Big Bang, after time equals 0. And if you convert 500,000 years to seconds, you get 10 trillion seconds. Sounds like a lot, but it's 500,000. It's not a tremendous amount of time. Now, what we're trying to do is unravel the quantum gravity epoch, when the universe was dominated by a very exotic field called the inflaton. This is a quantum field, a quantum scalar field for you playing at home experts. And this quantum field has properties like any other quantum field, in that it has fluctuations, it has ripples, it has uncertainty associated with it. It can't be uniform. It's impossible to have a quantum field be perfectly uniform everywhere. That is not allowable. So this field suffused the universe. Perhaps it suffused an even greater extent of space-time called the multiverse. But as I said, I'm not going to talk about the multiverse. But if inflation is true, most cosmologists believe that there is a multiverse, and that we, just as we are just one planet out of 8, at least in our solar system, and just as our sun is one star out of 100 billion in our galaxy, and just as there's probably 100 billion galaxies or more in our universe, there may be 100 billion universes within the multiverse. There may be 10 to the 500th universes in the multiverse. There may be an infinite number of universes. And so that really is quite mind-expanding to think about. But again, I want to keep bringing things back down closer to home, always thinking about dust. Always got to have dust in the back of your mind. So what would this be like? We're trying to take a picture taken at 10 to the 13th seconds, infer from it what the universe looked like 50 orders of magnitude earlier in time. What is that like? Well, it's like taking this object here, which is a collection of human stem cells called a blastocyst, which represents the way that you looked 1,000 seconds after the Big Bang that produced you. This object here was produced, and then later on it evolves, right? It grows and it evolves inside of your mother. Now, I couldn't take a picture of all of you guys here, but I want to add some identifying features for you to guess who this person might evolve into someday. So I add those, though it's not Andy. It could be like Andy, but it's not. Instead, it's my son's favorite astrophysicist, Neil deGrasse Tyson. Okay, now that really hurts. Okay, I have to tell you, I have to be honest with you. It's very painful to admit that. Now, Neil, good old Neil, who's a fellow co-author in my publishing house, I like to say that between Neil and myself, we've sold about 1,005,000 copies, so that's pretty nice. Now, this image represents Neil, about 60 years old. Convert your age to seconds, he's about 2 billion seconds old. This object's about 1,000 seconds old. That's an extrapolation of only about 2 million. This is an extrapolation of 50 orders of magnitude, 44 orders of magnitude more challenging, and yet we think we can do it. In fact, we think we had thought that we did it. And I want to explain what happened. So the image that I want you to keep in your mind, so we stretch beyond what Galileo saw, which was down here, to the realm of the nebula, galaxies, and clusters of galaxies. There's the so-called cosmic dark ages. There's the CMB. But what produced the CMB? We think the best candidate for that quantum field that caused the universe to have the features that would later grow into these anisotropies, these fluctuations, later grow into these galaxies and clusters of galaxies, later evolve into individual galaxies, stars, planets, and people. That's called inflation. If you could prove inflation happened, in some sense, you would also be proving, as I said, that the multiverse hypothesis is true. So the stakes are very high. Now, how do you do it? I'll ask for your trust that you can't do it by purely looking at images of the temperature fluctuations of the microwave background radiation. They simply do not convey enough information. To get more information, you must use another property of light, and it's called its polarization. Light tends to align in different directions after it interacts with matter, and I'll explain that in just a second. So if you have a flashlight, an incandescent flashlight, it produces an unpolarized glow of visible light photons. If those photons interact with matter in the form of an electron here, it will cause it to oscillate in this plane here, and it'll oscillate randomly like this. If you have light if you view that light from another direction, you don't see that the light is moving in this direction only. You see it oscillating basically vertically, purely vertically. So you've converted an unpolarized light source into a polarized light source by scattering, by interaction, by a conflict or a collision between light and matter. That produces another property that you can then invert. If I see polarized light, then I can infer two things: that the light must have been coming in anisotropically in different amounts in different directions, and it must have interacted with electrons. So we know the early universe, a million years after the Big Bang, had a lot of fluctuations in light. We also know it had a lot of electrons, the so-called primordial soup, the plasma of protons, electrons, neutrons, croutons. No, there were no croutons back then. Now, if you go to lovely San Diego, so I invite you to visit, especially you Foothill College students who may be thinking about graduate school. Deadline 3 weeks from now. Don't forget to apply. Now, if you look at these waves, these are called gravity waves, not gravitational waves. These are fluid waves of gravity that are the result of changes in pressure and density of water. When light interacts with that, you can see the pattern of it, and actually the light will acquire a slight amount of polarization. And you can use that polarization to infer things such as the properties of this matter. Now, we know it's salt water, but you can actually use it to measure things like salinity, wave height, wave direction, what stimulated that wave to form. Remember, polarization teaches you about the interaction of light and matter. That's what's so fascinating, useful, and peculiar about polarization. And so we thought with our colleagues that we could use the properties of the earliest light in the universe as a sort of detector of phenomena that happened at the Big Bang itself, namely during the inflationary epoch. So light scatters off of electrons. That's called Thomson scattering. And there's a couple of different ways it can scatter. The most prominent one is called, or the most important one for the revelation of inflation is called B-mode polarization. I won't get into the details of B-mode polarization right now. Suffice it to say that if cosmologists were to see a swirling, twisting pattern of the polarization of light, we could infer that there are waves of gravity in the early universe, not water waves, but gravitational waves, just like LIGO detected, but not from two black holes colliding together, but if you like, all the matter and energy in the microwaves and all the pressure and sound waves, all those interacting with this resonance of space-time itself, detecting gravitational waves from inflation that would reveal the inflationary quantum gravitational epoch. Just an astounding discovery, if true. So here's a cartoon to keep in mind. And with this, we'll move into some of the telescopes, and then a little travelogue, and then back to the Nobel Prize, and then we will end with plenty of time for thunderous applause. Okay, this is the cartoon to keep in mind. The Big Bang occurred, creating gravitational waves if inflation took place. Inflationary gravitational waves perturb the cosmic background radiation's polarization, imprinting a swirling, twisting pattern on it called B-mode polarization. This is what we would see if inflation ignited the Big Bang in the very earliest moments after the origin of the universe. To make this discovery, myself and my colleagues at Caltech created a telescope, which was later incremented, like Silicon Valley, iPhone 8, iPhone 10. We originally called it BICEP, then it became BICEP 2. We're currently observing BICEP 3, and the next generation of experiment, give you a guess at what it's called? Not BICEP 4, BICEP array, but that's a story for another day. This discovery made by this telescope set off a resonance around the world. But first I want to describe what this telescope did. It was very similar in spirit, and there's no doubt in my mind that Galileo Galilei would recognize our telescope as being almost identical to his with a couple of different modifications. But he would surely understand it. It's a refracting telescope, not 1 or 2 inches in diameter, like this little guy, but about 12 inches in diameter. And the lenses were not clear optical lenses. Wake up back there, I see you. Okay, don't nod off. But the lenses were not made of clear glass. Instead, they're made of high-density polyethylene, the same material used to make milk jug containers. This may not look like much to you. You may not be able to see through me, but if you could see the microwaves coming from my face, and yes, there are some microwaves coming from my face, you would see me either magnified or reduced or distorted in some way, the same way you would as if this were a piece of glass. These are the lenses. So far, so good. Very similar to Galileo's telescope. Where it differs from Galileo's telescope is instead of the squishy, wet detectors in the back of his retina, we use these very hard detectors printed on silicon, appropriate for this valley, but they're made of superconductors. They're a type of superconductor whose resistance changes radically with a slight, minuscule increase in temperature. These detectors, of which we only had 256 pixels, you laugh, but we had to cool these down to 0.25 degrees above absolute zero. So you can't do that with your iPhone and keep your warranty. That won't work. The Apple Store folks don't like that. Instead of putting it on the flimsy little tripod that Galileo invented, we put it on a massive 10-ton mount. And here it is here. It soon after acquired a Twitter handle. And then we had to deploy this instrument to not northern Italy, where Galileo was outside of Florence, but we took it to the very bottom of the world, Antarctica. The word, as I say, Antarctica, still sends shivers up my spine when I hear about it because of all the stories I had heard about the great hardship that the initial discoverers of this frozen continent encountered, many leading to their death. So here are the first two teams to ever reach the South Pole. One was led by Norwegians, and they employed a special type of technology that the British were somehow either too proud to utilize or too stupid. No, they're not stupid. Brits are incredibly intelligent. But they decided that they knew that the Norwegians, when they got to the South Pole, would eat the dogs. And the Brits were totally averse to eating dog. And so they decided to become the beast of burden themselves. So they sledged. Now, mind you, it's only 700 nautical miles. It's not such a big deal, right? And you only have to go from sea level to 10,000 feet above sea level, up giant glaciers and crevasses where you could die. And you're just carrying a couple 1,000 kilos of scientific supplies and collecting meteorites, which these guys didn't do. They weren't doing a scientific expedition the way the Brits were. And so when Scott's team, the British team, got to the South Pole, they were terrified when they saw this staring at them from miles away, a Norwegian flag. How about that? Our Norwegian flag. So they got there, and Robert Scott, he said famously, "Great God, this is an awful place, and all the more so for having reached it without priority," meaning that he hadn't been there first. And it really makes me think of how Nobel Prize discoveries happen as well. You can get all the personal satisfaction you want from being the second person to discover something, but unless you're the first, unless you get there first, you don't win the golden medallion that I'll talk about later. There are a lot of parallels between Antarctic exploration and the pursuit of scientific knowledge. Now, what must have this felt like to Robert Scott? Now, there's a movie out recently creating a lot of controversy called First Man, where they don't show the American flag on the moon for some reason. Now, this is not meant to evoke that. This is meant as a thought experiment. Consider what it would have felt like for Neil Armstrong and Buzz Aldrin to step out of the Eagle lander and see this awaiting them. I mean, they would have been devastated. They would have been drinking, Tang for days. Now, so it's still very dangerous to go to Antarctica, and we don't get you don't have to deal with many of the creature comforts that they enjoyed 100+ years ago. But as I said, it's still very dangerous, as these videos that I've brought with me tonight demonstrate. So there's a penguin there, which my 5-year-old always says, "Daddy, bring me back a penguin when you go there." And that's very cute, but it never happens because they're vicious beasts, okay? You think they're cute? They're not cute. They're terrifying. And if you think that's bad, they treat their own kind even worse, as this video demonstrates, okay? So they're not, as I always say, it's still friendlier than most of our faculty meetings, okay? But anyway, now when you go to the South Pole, you have to bring everything with you. There are no Costco's down there, there's no Walmarts, you can't pick up stuff, you have to bring it all with you, and you have to wear most of it on the flight there. So the thought is, I guess the rationale is, when your plane crashes, the sharks will be less likely to eat you if your body is slightly warmer than the surrounding temperature. But here we are, we're going to the South Pole, we're going to Antarctica. This is the New Zealand Air Force, about 10% of the entire New Zealand Air Force. It's a C-130 airplane. You can barely see back here, but you know, the United States Air Force has a formidable mascot, the screaming eagle. Terrifying, right? Raptor, disgusting, or very terrifying, right? Now, what is the mascot of the New Zealand Air Force? You can't really see it, but it's the kiwi bird. Okay, a flightless bird. Doesn't instill too much terror in the hearts of its enemies. But that just shows you New Zealanders don't have many enemies, okay? Except for Australians, so they don't like Australians. Now, you get on the plane. This is what the inside of a C-130 cargo plane looks like. There's barely one window on the entire passenger class. This is your entire in-flight meal. You have your in-flight entertainment. You sit like this with your bags around you. There's no bathroom flushing toilet on the plane. There's a bucket in the back called the honey pot. I'll leave that to your imagination, why they call it that. But at least it's only for 11 and a half hours. It's not so bad. Really, I've been on Southwest flights that are worse. When you land at the South Pole, eventually you make it there, you go by another type of flying snowmobile called the LC-130, and you see the telescope that you've spent years working on. That was BICEP. BICEP stands for Background Imaging of Cosmic Extragalactic Polarization. And the reason I called it that is because what we're looking for is a curling, twisting pattern of microwaves. Remember? That's the B-mode polarization, also known as curl polarization. So biceps do curls, and I thought it was cute. Now, when you land, you're treated to the South Pole's finest passenger terminal. Here's the Admirals Club is over here. President's Club is there. You get points and money. No, you don't. Now, remember, Scott said this was an awful place. I flew there. It took me 2 days, but the total flying time is only about, say, 14 hours from New Zealand to get to the South Pole. Not so bad. It took them months to get to the South Pole. They end up dying. And as I said, they had to go from sea level to 10,000 feet, over 700 nautical miles, and they knew they were racing the clock every moment. And it wasn't just like cross-country skiing like you might do in Tahoe. It was over these frozen waves of snow called sastrugi, over crevasses, underground caves that could collapse at any moment, taking lives with them. So that's what it looked like back then. This is what it looks like when I went. Okay, I say it's an awesome place. And we have a station there funded by you folks, the tax-paying public, that the National Science Foundation has put together and allows research by many countries, not just the US, as long as they're doing scientific research. You can't go there if you want to do anything commercially or militarily. It's an entire continent off limits to that kind of exploitation, which is kind of cool and idealistic. Of course, in the winter, there might only be a couple hundred people on the whole continent. And so some people spend an entire year there, during which there's only one sunrise and sunset. And so we like to say, when we want someone to work there, we'll pay you $70,000 for one night of work. And you'd be surprised, a lot of people take us up on that offer. Here's the very axis on which the Earth is turning. So right here, the Earth's axis goes through, so you can run around every time zone on the Earth in a second or two. It's just an amazing place to be. It can get down as cold as 100 below 0 Fahrenheit. It can get as warm as, basically 0 Fahrenheit or thereabouts. Huge temperature changes. It's just an amazing place to be, like a frozen planet from, Star Wars or something. So here's what I like to call the second most important building at the South Pole. This is the Dark Sector Laboratory where BICEP 2 live. BICEP 3 lives. It's the second most important building. There's the first most important building. Okay, the outhouse. You gotta respect the outhouse. Now, you notice the buildings are built up on stilts. Although the outhouse isn't. That would be a trick, to have a 2-story outhouse. I don't know how that would work. It'd be kind of disgusting, I'm sure. Better than a honey pot. But this is built up on stilts because if not, snow will eventually overcome the building. And that's happened with many of the old buildings built in the 50s. They don't really know where they are because they built them on the surface of the snow. And every year there's feet of snow that build up from snow blown across the entire continent of Antarctica. To avoid that, they build it up on stilts. So we look for this signal, this curling, twisting pattern of microwaves. And on March 17th, St. Patrick's Day, 2014, we announced we made the discovery of the thing we were looking for, detection of B-mode polarization at degree angular scales using BICEP 2. So this was a phenomenal achievement. Everywhere around the world resonated to this discovery. Up the road at Stanford, there was a video posted that same morning of the announcement, and they garnered 2 million hits within a couple of hours. Just phenomenal. This is with one of the theorists credited with some of the early discoveries of the theory of inflation. Hearing the announcement from one of my colleagues, Professor Chalin Kuo, that we had discovered this theory, and the proof of this theory essentially, that inflation was correct. Remember, inflation, multiverse, incredible, mind-blowing discovery. Press conference at Harvard, filled with Nobel laureates in the front rows there. We made headlines around the world, including the newspaper of record, the San Diego Union Tribune, and other newspapers, front page, above the fold, as they say. Space ripples, seen as the Big Bang smoking gun. There's me looking wistfully. I like this headline in The Economist, because it kind of sounds like just some dude is watching. Oh, that man saw the beginning of time. Well, that's not what happened, but it's also, none of these really compare to my favorite headline in The Onion. Okay, so The Onion is the premier science newspaper, of course, in all of the world. And they convened a panel, they said, of top theoretical physicists and R&B singers to debate the meaning of forever. The caption says, panelists discuss whether it is theoretically possible to give you my heart forever. And down here, we can observe long-term phenomena like the CMB, primordial B-mode polarization, and the love between India Ari and her man, all of which seem to have existed since the universe's infancy. Now, we can all, in this auditorium, we can start to smell that something's not right. Actually, you can actually smell what ended up getting in the way of our discovery, right? You can sort of smell there's smoke in the air. That smoke is just like the dust grains that eventually would be seen as the cause of the signal we imputed to inflation. So within months of discovery, we started to get attacks that I describe in the book as the most traumatic, perilous moments of my scientific career. Hearing that we may have made a colossal, universal mistake or a blunder. And people were criticizing us from all angles. And it was up to us to really uncover what was wrong or right and back up our findings. Eventually it came to be through collaboration with a competitor of ours, a satellite called the Planck satellite, launched by the European Space Agency. We worked together to discover that the signal that had been twisting and curling the microwave polarization was nothing more than grains of cosmic smoke, dust grains in our galaxy. Not unlike the dust grains that Galileo was befuddled by, and Herschel before him, and later Hoyle, and many other scientists throughout cosmic astronomical history. These grains of dust can acquire a tiny bit of magnetism to them, and in so doing, become influenced by the Milky Way's magnetic field. So all things that we know about have magnetic fields. Galaxies have magnetic fields, planets have them, even people have them, birds have them. And you can use them for certain purposes, but in this case, they exactly mimic the signal we were seeking. And we couldn't have known it at the time because we weren't able to access the data we needed to prove or disprove our claim of detection. So we went ahead with it, we put in some caveats, and eventually we had to retract that. And that was very humiliating, but at least we knew what we had seen was not the pristine view of the cosmos, looking out from the South Pole all the way back to inflation, but in fact, the universe is a pretty smoggy, smoky place, that there's dust on almost all size scales in the universe, from planetary scales up to galactic scales, and even in clusters of galaxies. And for astronomers to look back and read the prologue of the Big Bang, we have to look through a lot of dust in the dust jacket of the cosmos. Now, I don't want you to get the impression that dust is all bad, because as the late, great Carl Sagan said, without dust, we wouldn't be here. So it's a famous poem that he wrote on the occasion of the Voyager satellite taking a selfie of the Earth from beyond the orbit of Saturn on Valentine's Day 1990. Here's the picture. It's called the pale blue dot. And Sagan says, we succeeded in taking that picture. And if you look at it, you see a dot. That's here. That's home, that's us. Every saint and sinner in the history of the species lived there on a mote of dust suspended in a sunbeam. Very poetic. What is he saying? The Earth is just a giant grain of dust, or ball of dust. And even the dust can do things like form from the iron within a type 2 supernova. And that iron can eventually make its way into the Earth and into your mother and into your blood in the form of hemoglobin that flows through your veins right now. It's just astonishing, this interconnectivity. As Sagan said, we are all stardust. I like this picture taken by my friend Brent Rose that shows cosmic dust. This is dust in the Milky Way galaxy. These are lanes of dust. The planet, this kind of mesa-looking thing over here, and people, two figures that you can't see. They're made of dust. And the planet's made of dust. And the Milky Way is pulsating with dust. It's just amazing to think about how important dust is. As I said, it's far more important than a wormhole. And we have far more evidence that it exists, unlike a wormhole. And so things that are exotic are fun to think about, but first you have to get past the darn dust jacket. So along with the dust kind of blowing in the interstellar wind went my chances at Nobel glory. Blown away. But, fear not, for just a few weeks after retracting this in this embarrassing event for myself, but it was part of a healing process within cosmology to reconcile and rectify the discoveries that we made with what was actually happening. We didn't make a blunder. We didn't leave the lens cap on or forget to connect a fiber optic cable. We didn't make a blunder. We imputed an origin to the signal that we saw that was incorrect. And now we know that there's even more evidence than ever for the reality of the signal we saw. We believe it. Everybody believes that we were right. The interpretation was wrong. But being a good scientist means you have to reconcile what you say with the data that you have and try to be as immune as possible from this confirmation bias as you can be. As I said, a couple of months after this retraction, I received a letter from the Nobel Committee for Physics inviting me, Professor Brian G. Keating, the honor of nominating winners for the Nobel Prize in Physics for 2016, okay? So imagine you're here and you're a realtor. Any realtors in the audience? Any lawyers in the audience? Okay, can you go over there, please? No, that's fine. I love lawyers. Hubble said I'd rather be a second-rate astronomer than a first-rate lawyer, but I love lawyers. So imagine you're a lawyer, client comes to you, prospective client, says, I'd like to hire you, get your services, but actually I don't like you that much. Can you recommend a better lawyer? It wouldn't feel so good. And that's what I felt like when I got this letter in the mail. And it asked me to do a couple of things. It asked me to consider work done long ago for multiple people, candidates in plural, to be worthy of the Nobel Prize in Physics. Now, I'm an academician, so I went back to the original source material reading list itself, Alfred Nobel's will, handwritten in Paris the year before he died, remember? And I speak fluent Swedish, as you all do, I'm sure. No, it's helpfully the Nobel Foundation translates it on the website, and if you translate it into English, it says, the whole of my estate shall be annually distributed in the form of prizes to those who, during the preceding year, shall have conferred the greatest benefit to mankind, apportioned as follows, 1 part to the person who shall have made the most important discovery in physics. So a single person who made a discovery last year that had the greatest benefit to mankind. That's a pretty tall order. So for inspiration, I went back and looked at different Nobel Prizes won in the past. So I gave this talk at the San Diego Astronomy Association's meeting, and they all got this right, so I'm counting on you all to get this right. I'm going to ask for a show of hands. One of these discoveries won the Nobel Prize, 2 did not. Who thinks the Nobel Prize was won for the discovery of the RNA molecule? All these were eligible for Nobel Prizes. Very good. Who thinks number 2, the periodic table, which has, I remind you, element number 102, nobelium. Who thinks number 2 won the Nobel Prize? Who thinks number 3, the lighthouse, won the Nobel Prize? Okay, not everyone. So anyone does not like raising their hand in public, please raise your hand. Of course it's the lighthouse. Come on, people. Because the lighthouse is so important, it creates a great benefit to your life. And Gustave Dalén won it for the invention, not just of the lighthouse, but for the invention of automatic regulators for use in conjunction with gas accumulators for illuminating lighthouses and buoys. Whew, that's really impressive stuff. Now, I got here using a lighthouse, as I'm sure many of you did. You don't need a GPS, you just use a lighthouse, right? Now, this is big stuff back then. Now, he was Swedish. He invented it the year before, a single person. It had a benefit to mankind, so it's perfectly in keeping with Alfred Nobel's wishes. So I thought that's pretty interesting. Now, there have been controversies beyond those controversies. So nowadays, we're hearing rumors of Nobel Prizes, not this year, but next year, for our fearless leader, right? We are also hearing things that are not so funny. So we're hearing about rampant allegations of sex abuse that led to the cancellation of the Nobel Prize in Literature for 2018 and may lead to its cancellation next year. The King of Sweden stepped in and implored the Nobel Academy to change its rules in order that the Nobel Prize could undergo a period of reflection, re-examination, to rectify these past wrongs. The last thing I want to talk about is getting slightly better, which is the first sentence in Alfred Nobel's will says the following. I, Alfred Nobel, do hereby mature, give my last testament, to my nephews, Jlamlar and Ludwig Nobel, I bequeath the sum of 200,000 crowns, To my niece, Mina, 100,000 crowns, okay? So the women got half as much. He had no children of his own, by the way. He had no wife, no spouse, nothing, never married. So these were all his only living heirs. He gave half as much to the only girl in his life, woman in his life. And some say that's the origin of the Nobel Prize in Physics' legendary sexism, where fewer than 1% of all laureates have been won by women. Luckily, this year, the trend was broken, so that's quite awesome. Still, we can list all the 3 women who have won it in the past 117 years on one slide, fit them all there at their names and everything, the years they won it. And everybody's rightfully celebrating Donna Strickland's award that was given out this year, and she'll receive it on December 10th, which is the anniversary not of Alfred Nobel's birth, but of his death. Kind of weird. But anyway, they celebrate and give away these prizes on the day he died. And I like to point out, this is great, but they would need to give the Nobel Prize to women, only women in physics, for the next 75 years to have an equal number of male and female laureates. So there's still a huge, huge gender imbalance with the Nobel Prize. So much so that even this year, when the chemistry prize was shared by a female, a professor of physics at Caltech, this is the headline at JPL, the Jet Propulsion Laboratory, a couple of days after she was awarded the most prestigious accolade in humanity has to offer. Caltech mom wins Nobel Prize. And actually reminded me, I met Maria Gephardt-Mayer. She was at UCSD when she won the Nobel Prize. I met her son on the occasion they dedicated a stamp for her discovery of the world's longest slide rule. No, she discovered the nuclear structure and the so-called magic numbers that describe nuclear stability, won it in 1963. Her son Joseph said to me, when my mother won the Nobel Prize, the headline in the Union Tribune, or whatever the newspaper was called back then, said, "Local housewife wins Nobel Prize." So there's a long way to go. This just depicts this. So there was a huge uproar about this. A couple hours later, they took it down. I'm glad I got a screenshot. And I want to close by describing an event that I participated in, which was upon the occasion of submission of the first draft of my manuscript for losing the Nobel Prize, my cosmic memoir. I submitted it. This gentleman, Duncan Haldane, came to UCSD where he had done the work that garnered him the 2016 Nobel Prize, the prize that I was supposed to nominate him for. Don't tell him I did not nominate him. Actually, nobody's supposed to know, I forgot to tell you guys, nobody's supposed to know that I was one of the nominators of the Nobel Prize that year. Don't tell anyone, okay, please. Please, you're doing me a huge favor. It said strictly confidential. He brought his Nobel Prize with him to his colloquium. And there were people there, physicists, young and old, idolizing the Nobel Prize. Not him, the Nobel Prize itself. Taking selfies with it, kissing it, bowing down to it. It really made me think of the episode of the golden calf, where people make an idol out of something themselves and then worship it. And it made me kind of nauseated, to be honest with you, that physicists, the most brilliant, the most rational members of humanity, could be so base and craven to their desires to worship a golden image. It made me quite embarrassed, actually, and I felt so terrible. Oh my God! So even I, who had written a book about the evils of the Nobel Prize in some sense, or the perils that it's causing on scientists and society, I could not resist the temptation to pose for a selfie. And he's a wonderful guy. I don't have any problems with any of the winners. It's the process by which it's awarded. And it's so much so that society likes to elevate winners, like American Idol and the Oscars and so forth, that even it hits scientists and mathematicians. This happened just this past summer. The Fields Medal, which is called referred to as the Nobel Prize for Mathematics, so there is no Nobel Prize in Mathematics, but this is called that. It was stolen minutes after it was awarded. So why would you steal some piece of metal that it's worth 15 grand, okay, and that's nice, but obviously that wasn't the reason that somebody wanted to make off with it. It's 15,000 Canadian, by the way. But it did, I feel terrible for the guy who got, he eventually got a medal back, but it gave me an idea for my next book's title. Okay, this is great. Stealing the Fields Medal, coming soon from Brian Keating. There it goes, woo! Okay, I want to conclude with a couple of words about where do we go from here in cosmology and in the Nobel Prize. First of all, refer to Mahatma Gandhi, nominated 5 times for the Nobel Peace Prize, never won it. Hitler was nominated once, also didn't win it, thank God. Mahatma Gandhi said the seeker after truth should be humbler than the dust. The world crushes dust under its feet, but the seeker after truth should so humble himself that even the dust could crush him. Only then, and not until then, will he have a glimpse of truth. It's kind of beautiful. It's saying, don't only pardon our dust, but embrace the dust. Get down and dirty with the dust. And in doing so, we can do great things. We can make discoveries cognizant of the role that dust plays in the universe. And how are we doing that? Well, I'm privileged to be leading a project called the Simons Observatory, made up of about 240 of the world's most brilliant scientists. And here's a list of places around the world where we have bases that are working on this project. It's funded in large part by these two foundations, one of which is located not far from here, the Heising-Simons Foundation. It's a $70 million project to look out into the universe, not only for the wispy imprint of inflationary gravitational waves, the multiverse, et cetera, but also at dust. How do we do that? Well, the $70 million that we've received is being used to build a gigantic space vacuum cleaner. Now, you're laughing. Okay, no, we're not doing that. That would be ridiculous. Instead, we're building telescopes. And instead of only looking at the cosmic signals, we're also spending a lot of our time looking at dust and then removing that dust, because you can't build a cosmic vacuum cleaner as much as I would like to. Here's where it's going to be located on a plateau not far from the Simons Array project, led by myself and Adrian Lee at UC Berkeley, and not far from the Atacama Cosmology telescope over there. And it's going to have an array of telescopes, each one more powerful than the BICEP telescope, cooled down to 0.1 degree above absolute zero, just an insanely cold temperature. What we're going to do is observe at multiple frequencies and dedicate some of the observing time and effort into only looking at dust. As Mahatma Gandhi said, you want to be humble that the dust could crush you if you don't account for it. Some of these telescopes are basically purely looking at dust. Afterwards, we can remove it. And what we're left with, hopefully, will be the pristine signal we were seeking all along. Here's just the design. It's another refracting telescope, just like my BICEP project, except cooled down much lower. It uses a very special type of detector technology built up the road at UC Berkeley that is a fractal type of antenna that can see multiple frequencies at once. And then there's another detector system built by the National Institute of Standard and Technology in Boulder that does essentially the same thing, not with a fractal spiral antenna, though. Okay, the last thing I want to say is what was the final sentence of Alfred Nobel's will. Alfred said, "Finally, it is my express wish that following my death, my veins shall be cut open. And when this has been done and competent doctors had confirmed clear signs of death," by the way, if you cut open your veins, you're definitely dead, okay? That'll be the clearest sign possible. And then if you want to be really overkilled, then you take your remains and you cremate them in a crematorium. I have no idea, given what they've done with the will that Alfred Nobel specified, it should be given to a single person who did something in the preceding year that had the greatest benefit to all of mankind. I have no idea if he's cremated, if he's stuffed somewhere, or where he is. Okay? I'd like to think that they adhered to this will, but it made me think, and it's part of the motivation for my book's title. One title aspect of it, the title is a double entendre, as the French would say. One is how I personally lost the Nobel Prize, came within a hair's breadth of winning it, lost it ultimately. The other meaning is what should be done to the Nobel Prize to better reflect the way that science is done today, not in the late 1890s. So I hope that you'll be able to check the book out and come along on a cosmic journey of discovery, revelation, and most importantly, of dust. Thank you very much.
If you had won the Nobel Prize and had that oops moment, would you have got to keep it?
So would I have gotten to keep it? So I like to say, people say, well, you just kind of have sour grapes about this whole thing, and you're not really, telling the truth. And I say, well, if you want to see if I'm sincere, just award me the Nobel Prize and see if I reject it or not, or I'm a hypocrite. So I suppose I would have been able to keep it. The instructions, beyond saying complete opposite of what Alfred Nobel asked for, they had a very clear insert that said, you may not nominate yourself. So I took that very clearly, and at that moment, I think we were clear in many ways that we needed to get confirmation of our discovery for it to hold up, to be even eligible for myself or anybody on the team to win a Nobel Prize required confirmation which never came, and is still elusive. That means the signal's out there to be discovered. But I claim that even if I do discover it, I shouldn't win the Nobel Prize for doing so, because there's just too much temptation when you're looking for a signal to find it and overlook evidence to the contrary. And so I think that discoveries like that are more like the discovery of dark energy or dark matter, for that matter. Those are the types of discoveries, serendipitous discoveries, that should truly warrant the Nobel Prize. Thanks. There's one over here.
Could you please elaborate about on your slide about polarization? You have E mode.
Yes.
E mode.
Sorry, you want me to show the slide?
Yes, yes,
Okay.
yes. And could you explain like what's on the axis, like horizontal axis and vertical axis? So I can see this topologically. You have plus one defect, and on the right side it's something like different. So
Let
could
me
you
see here.
explain?
So there's two different types of polarizations. There's what's called E mode polarization, and there's B mode polarization. So without getting into too much detail during this period, let me say that gravitational waves, shown here, gravity waves, what they do is they cause space and time to be sheared. So they also cause a compression and a rarefaction of space-time. That's basically what LIGO discovered, that the two arms of its interferometer were squishing and squashing in a certain way. But you could also have a wave of gravity that causes them to shear a slight amount. And the early universe would have been populated by equal amounts of polarization that would squish and then that would shear. And only the shear terms can create this pattern down here called B modes. So the compression and rarefaction produces what's called E modes on different phase planes separated by 180 degrees. And the B modes can only be created by waves of gravity. And that's because they're the only things that can shear space-time over cosmic distances. And so for that reason, they're referred to as the smoking gun of inflation. They're the only things that can be produced on cosmic scales, equal amounts in all directions at all times.
This is like light coming in the multiple polarization on the white picture?
This
or-
is showing light coming in that's unpolarized in two different directions, hotter over here, colder over here, scattering and producing a polarized signal and the outcome. This is called Thomson scattering. That produces polarization of any kind, E mode or B mode. So the question is, how do you get this anisotropy of the light? There's multiple ways to get it. One way is from the compression of space-time itself.
But from the symmetry principle, would you also get minus one?
So yeah, so
effects?
the minus one, so this is like plus one and this is like minus one.
This is
Positive B mode, negative
This
B
is
mode.
also plus one, isn't it? Just different phase.
There's two spin numbers. We can talk later. The gravitational waves have two different polarizations, plus and cross, and the cross ones are contributing here.
Okay, thanks.
Yeah.
Is space-time really flat everywhere you look? Is there any kind of anomalous regions where LIGO would maybe help you identify
Yeah.
using BICEP or
So-
similar
so-
technology?
There's something called the cosmological principle, which says that space-time is flat over cosmic distances. On a scale of, you go past megaparsecs, that space-time becomes uniform and homogeneous, meaning that not that there's equal amount uniform distribution, it's just that the statistical properties are constant, like the air in this room. I can't tell you if there's a molecule right there, but I can tell you in a box there'll be an average of so and so many molecules, and between them there's empty space. So on the scale of molecules, it's not uniform. It's highly non-uniform, inhomogeneous. But on the scale of my hand or a volume, it is. And that's what we call temperature and pressure. In the early universe, this pattern here is statistically isotropic. It's the same on all different scales once you get beyond a certain scale. So on cosmic scales, the universe is flat. On local scales, it's not. Actually, I think there was a talk here not too long ago which talked about gravitational lensing, which is the bending of space-time by matter. And it was in fact predicted by Einstein that he thought would never be discovered. And we're actually using that property to infer the properties of other aspects from the microwave background. So yes, you're right. It's flat on the larger scales, but highly non-flat, non-uniform on the scales of galaxies. Another question over there?
Thank you for a very entertaining talk
Thank you.
and informative. So I have a general question in cosmology, if I may. I read that a distant object, when it emits light, even when it emits the light, when that object is moving faster than the speed of light relative to us, that light still reaches us. Is that true? And if so, how do you look at that? How do you think about that?
So it's not true that there are things moving faster than the speed of light. The universe, the outer boundaries of the universe, the observable universe is receding away at a speed that is greater than the speed of light. It's highly redshifting the light that we see. That's why the microwave background is reduced in energy and in frequency by a factor of 1,000 since the time it was produced. As the universe has cooled and expanded, there are regions beyond which objects like galaxies are moving away from us faster than the speed of light. Now there's another phenomenon which I thought you were going to ask about, which is what happens when a particle is moving fast through a medium like ice, is moving faster than the speed of light in that medium. So media like this lens or water, it slows down the speed of light by what's called the dielectric constant. And so you could have a particle, theoretically, that's moving faster than the speed of light, like a neutrino or something like that. It can emit what's called Cherenkov radiation. It's kind of like a sonic boom. The analog of a sonic boom for light is Cherenkov radiation. I don't know if that's what you're asking, but there aren't, we don't have like, we don't see objects, say, moving locally to us that we could somehow communicate with that are moving faster than the speed of light.
No, my question was, if you consider a galaxy, say, for example, so far away now that it is moving faster than the speed of light relative to us, and it emits light now, well, that light will reach us in the future, I'll read.
No, there's a horizon beyond which we won't be able to see, right? So
That's not true.
There's an analog, yeah. It's not unlike, say, the situation where an astronaut is falling into a black hole. When that astronaut gets close to the black hole, there's a gravitational redshift. So you could still see light now, but if somebody is shooting a beam of light from that galaxy to us today, that's very different than, say, as I said, as an astronaut falls into a black hole, you'll see the last image of that astronaut as long as there's light, but it'll be highly, highly redshifted. And so we'll impute from that a great distance. And so that's how we actually invert that. To measure the distance to objects and that recessional speed, we use the redshift. And that tells us what fraction of the speed of light it's moving. So something moving that's at a redshift greater than 1 is moving relative to us faster than the speed of light, meaning the universe is expanding faster than the speed of light.
Thank you.
Sure. Any other questions? Yeah.
Hi. I was wondering, what was it like to compete with another team for that Nobel Prize?
Yeah, well, I talk a lot in the book that competition has good things, and it's good not to have a monopoly where there's only one person, they can do whatever they want, or one group. It's good to have a variety of different resources, but at the same token, there's so much emphasis placed on priority of making the discovery first. And when you do make the discovery, getting more access to resources, to getting more access to publicity, getting access to really perks, including one which I didn't even know about until I started writing this book, which is if you won a Nobel Prize, you're automatically entitled for the rest of your life to nominate winners of the Nobel Prize in the future, which is a perk that nobody else gets. So what ends up happening is that if you work for somebody who has a Nobel Prize, or were the teacher of somebody, or you're much more likely yourself to win the Nobel Prize. So it's kind of this Matthew effect, the rich get richer. And I think that distorts the way that science is perceived, because that's not really the way that science is done. There's not like some oracle and only he or she knows everything and you must learn from that person. So there's always competition. Healthy competition is good, but when it becomes the really sine qua non of how you're going to be evaluated. I was told to get tenure I needed to win a Nobel Prize or be on track to win a Nobel Prize. And the woman who won it this year, Donna Strickland, she wasn't even a full professor when she won the Nobel Prize. So she won the Nobel Prize, then the next day they made her full professor. Okay, there's another perk. Hopefully she'll do better than Galileo when he got it. Maybe two more questions. Okay, is there one more over there? Yeah?
I wonder, this sort of follows on what you just said, but I wonder if not only, the Nobel Prize is perhaps symbolic of the whole framework in which science is done. And I wonder if there is a need for an overhaul of the entire framework, including funding and other aspects. And secondly, after your book, do your ideas have a lot of, are there other physicists who agree with you? And is there a lot, do you hear a lot from physicists who agree with you after your work?
Yeah, good question. Yeah, so the first point, yes, I think the Nobel Prize needs to be overhauled and reformed. That's the meaning of the second meaning of the book's title, that it needs to be lost in its current form, resurrected in another form. Meaning that you should use its prestige to agitate for improvement. And I think, look at Hollywood, look at the Oscars, look at politics, look at the Me Too movement. All these things, were suffering because they essentially had a monopoly on their industry. The Nobel Prize is the biggest monopoly. There's no close second in science and elsewhere. And so yes, I think that there's a great need for it. I outlined 5 key ways to go about that in the book. The book is mostly not about the Nobel Prize. I was surprised by my publisher. I said, I want to print there's only 3 chapters out of 13 about the Nobel. I said, can you print the sides of the pages and the chapters about the Nobel Prize in gray so people can skip it if they don't want? They said, sure, we can do that. And I was like, wow, okay. Cool, better than the dust jacket. But when we ended up writing it, I ended up getting a lot of positive feedback that everybody agreed with most of my suggestions, except for the one I make about serendipitous discoveries, that I say that those are the most pure scientific discoveries, because you're not looking to make a discovery. You accidentally discover something, and then you beat the hell out of it to make sure you understand it better than anyone else. I think those are the purest discoveries. Those are also some of the discoveries that have been left out of the Nobel Prize. Vera Rubin discovered serendipitously dark matter. Jocelyn Bell discovered pulsar serendipitously. Her advisor won the Nobel Prize, her male advisor, for Jocelyn Bell's discovery of pulsars. But that was serendipitous. She put in a ton of hard work to figure out what was it that she saw. And I think that that's brilliant. Great. Thank you all very much. I'll be outside to sign copies of the book. And I have special bookmarks made of real fake Nobel gold for any purchases of the book tonight. Thank you guys.